Just to cap. Well, actually, let's back up even a little bit. Functions. Function takes an input. X is the default, sort of symbol thing we use for that. Not important that it's an X, but the most frequently. Independent variable, variable because it changes, right? A function takes one of those, applies some kind of processes to it, right? And returns an output, y value, function value, value of the dependent variable that goes with the whole idea is that we're looking at how these two things change together. So graphically, x, y, say this is some function. Study the input or start. So that's how functions function notation. F of we'll just call it f of x equals 1. If I want to know what f of 5 is, plug it in, evaluate, right? Wherever this appeared, replace it with this. Then simplify. Same thing's true if the variable shows up more than one. Another example is called, say it's x negative 1. Wherever there was an x before, now I'm going to fill in. I can clean up or simplify that. One minus 2. And again, what that represents is a point on the graph of the thing. Right? It passes through the negative 1. Whatever else it does. And if we wanted to, we all okay with ideas, how that works. Okay. Well, that same function You plug it in, you do the exact same thing, only when I wrote a 1 before, now I'm going to write an. That's the evaluating part. I just write a thing that has the same, sort of shape as the function. Everywhere there was an X before. And then again, we simplify. That's g of negative x. All right, now what we talked about yesterday is how we can interpret that. There are two special classes of functions called even functions, odd functions, with special properties. Properties are that even functions are y-axis symmetric. Odd functions are origin symmetric. Properties of the graph, for one thing, but later on, it turns out that there are a lot of other things. Functions. The way those symmetries show up in the algebra, the way that looks symbolically or analytically, is that if I do the thing I just did and replace the input with its opposite, put the sign there, function is even, then we just end up back at the original function. So all those signs basically just it's not exactly the same thing as the function. It is not because it's not identical. Right? Quality of the checking. Odd functions are origin symmetric. Being origin symmetric again. Yep. That looks like in the algebra. That those things are opposite. So if I plug in negative x and I do whatever needs to be done and I clean the thing up and simplify, I end up with a negative sign that I could factor out of the work out front. What that means is that if it's a bunch of individual terms, they're all going to have opposite signs. And that I could take that negative. So we started with this. Ended up with this when we did that reflection and plug. Is this an odd function? No, not the same, so it's not even. It's not opposite in sign either. Right? Look at the individual terms. The first one's x squared here. First one's x squared here. Both positive, not odd because they're opposite in sign. Odd either. And that's sort of the like third possibility. So even and odd functions are different than even. Functions neither even or odd if you know what the word neither. Those two things identical. That's why it's not even. Sure. Example, say f is f of negative x. Same shape, so if x here and negative x here. Got x times x times x times x. Okay. Plus 2x squared plus 1. So we've done the evaluation part and we've simplified. This is f of negative x. This is what happens if I reflect over the y-axis. How did these things compare? They're exactly the same. What does that tell us? F is even function, and as a result has y-axis symmetry. And that tells me other stuff too. Right? If I did want to go so by doing okay. All right, cool. So in the last page is just a bunch of stuff about even and odd. So All right, let's compare notes on some of these real quick. 7, let's just say. Yep, good. So it's neither even nor odd. It has neither kind of symmetry either. Right? Maybe this. That one sort of subtly so. This, right? That one's neither. How about B? B is odd, has origin symmetry. Okay, C is even, which means it has y-axis. D, either E. F is. Okay. Are there any of those that we want to take a closer look at and talk about together? D? X squared? Okay. So if we look at a graph and we're trying to determine symmetry, might want to zoom in just a little bit. Happening close. So zoom in just a little bit. Origin symmetry. And the good news is that we don't have to rely only on the graphical interpretation to test, right, to check. Being able to look at that is good, but again, some of these, especially when you look at it a little bit too far away, like there, I can't really tell. Too far removed. I can tell when I look away. Okay about that? All right. Things symmetric with respect to the x-axis. Lots of ways you can do it. Here's one. Okay, never mind. I don't know how I made that happen. Thanks. Problem with thing like, correcting the shape for you. But no matter what you drew, notice, fails a vertical line test. Nature of the thing is that if you're symmetric with respect to the x, so is it possible for a function to be symmetric with respect to the x-axis? No, because it would have to fail a vertical line test. That's why we don't talk about a class of functions that has x-axis symmetry. So there is y-axis. that to help you do things, but it's not a. Okay, great. Right. About verifying analytically, again, by working out the algebra, that this is okay. It's neither. We know the answer already. That's good. How do we support the fact that it's neither? Plug in negative x, plug in negative x, simplify. What do we get? X squared is 2x. If I look at these two things, question is, are these identical? Negative f of x thing. Another way to say that is, hey, if you took the function, this one, and just threw a negative sign on the outside of it like that, out in front of the whole thing, like treat the function like it's one. Well, if I'm thinking about simplifying and stuff, what would I do with that negative? Distribute it. And if I distribute it, what do I get? Negative 3x squared minus 2x. This is the thing that would need to show up here in order for it to be odd. So when the so this one is, again, because of what we see. It has then none of the symmetry types that we. Like I have this question. Hey, here's a function. Tell me, determine. Make a big deal. So when I'm looking for this part, then all right. Now I assume that you feel okay then with like B, C, D because those are all going to. Right? The main one we probably want to talk about is H. Is there any of those others anybody wants to see? Fraction, sure. X. Okay, so negative X. What can we do to simplify that? Negative and a negative and a negative, so way fractions work, you can treat that sign as though it's in the top or as though it's in the bottom or as though it's outside of the whole thing. So compare these two things. What do we see? Sign change, right? This one looks a lot like the function we started with, but it's got a negative sign parked out in front. It tells us that this is an odd function, therefore has. Oh, of course, just reminder, my solutions are in Blackboard, so like don't feel like you need to scramble to write every bit down now, right? You probably prettier version of Blackboard. Okay, f of x is x times, kind of put this here for a reason. X the same, like that's in a set of parentheses. That means if I'm thinking order operation, what happens first? Parentheses, right? And the exponent is applied to that. Time we just don't get into it. Moving things into or out. So if I plug a negative x into this thing, what happens underneath? Negative x squared is x squared. And then the negative x. So I've sort of simplified this thing as much as I can. Like there's nothing else like staring me in the face to do to up. So if I compare to this, what do we see? That it's not, right? If I took this function and stuck a negative sign out in front of the whole thing, the way things are joined together here is by multiplication, right? It's x times pairs something, product, right? X times something. So if I stuck a negative sign out in front of this whole thing, it would just stay there. I don't distribute that because it's not addition, it's a product. There's addition inside one of those pieces, inside that square root, but because of order operation stuff, that happens earlier, right? So that negative doesn't get distributed. So this is actually an odd function. Doesn't look quite like most of the others that we